Thanks, Damien. So yeah, today I'll be discussing about the system design to support some of our Meta-designed inference accelerators on the existing Grand Teton platform. I'm from the platform hardware engineering team at Meta. This deck was put together with our TPM, release to production, and mechanical engineering team. So today, the main agenda is to kind of go over what Grand Teton MTIA system is, what are the main target workloads, the logical architecture of the platform, what the different boxes look like, and what the rack configuration looks like, and then go through in some detail about the individual components within the system. That's the accelerator module itself, the accelerator carrier tray, some of the expansion options that we've designed for, and a note about how we are leveraging the existing Grand Teton platform for other applications. MTIA is in-house Meta-designed silicon specifically for inference workloads, mainly for recommendation models. This talk is discussing the system design to basically house these in our data centers. This is our first generation inference platform, and we are leveraging the existing Grand Teton platform that we released a couple of years back to OCP. So this is the logical view of the system. We basically have three main blocks. The head node is a two-socket AMD CPU, two-socket AMD CPU with the motherboard tray has the boot drive, about 2 TB of DDR5 memory, 800 gig of NIC front-end bandwidth to supply traffic to the accelerators. This motherboard is then connected to an accelerator tray, which we call coal-to-bay, which is designed specifically for this use case. Each accelerator tray holds 12 modules or 24 accelerator devices, which are connected to the CPU through a Gen 5 PCIe switch. We also have an expansion tray in the middle, which can basically expand the host memory through CXL-based DDR4 memory. And we also have options to add additional flash drives and other PCIe expansion options from the PCIe switch. Overall, on the system config, we leverage the existing AMD two-socket head node that is designed as part of Grand Teton. The design is used as is. The carrier tray here holds 12 PCIe CAM modules, which are full-length, full-height dual-slot modules. Each module has 2 ASICs. The ASICs have on-chip SRAM memory as well as LPDDR5 memory on the board. So since our applications are memory heavy, the overall tray has about 1.5 TB of LPDDR5 memory. And then the host memory is kind of sized accordingly to support 2 TB, and then we have additional expansion options through CXL. So the overall system is a derivative of the Grand Teton platform that was designed for GPUs. We basically made changes to the accelerator tray and the expansion tray to support this use case. Within the expansion tray, we have multiple options. We can support CXL memory through 8 CXL modules and 4 flash drives connected to the PCI switch. Alternately, we can also reduce the number of CXL, increase the number of flash drives with the same baseboard. The same baseboard also supports connecting an RDMA NIC to the switch that is also holding the accelerators. This kind of modularity allows us to make late binding changes as and when our inference models evolve. This is the rack. Each rack holds 3 systems drawing about 15 kilowatts from the PSU shelf. The top of rack switch we use is the Wedge 400, which is also an OCP released hardware. The rack has a facility to make it more dense by adding another system, by using a higher powered PSU and more uplink, but this is a current production use case. There's a lot of OCP leveraged hardware in this rack. We use the DCSCM BMC modules for the motherboards, the NICs OCP 3.0 TSFF 400 gig NICs. The overall rack is ORV3, and the Wedge 400 variants are also released into OCP. This is the basic building block, the key block in the system, which is the accelerator module itself. Each module holds 2 accelerators with a dual slot thickness. This is mainly done to optimize the thermal support in the limited amount of space we have in the system. So that allows us to push the ASIC power higher than having 24 individual thinner PCI modules. So each ASIC can go up to 90 watts, and each module can draw up to 220 watts. We have a 12-volt high-power connector to support that. So this is more of a power-optimized system. So each ASIC has PCI Gen 5x8, which are routed to the PCI Chem connector, and we made some changes to the PCI Chem slot to support some additional MTIA specific interfaces like USB for debug, and some additional signals to support the two end devices per module use case. Within the ASIC, we have quite a bit of SRAM to support high bandwidth memory. Each ASIC has about 256 MB of SRAM, and of the ASIC, we have 4 60 GB LPDDR5 devices connected to each ASIC. The module also has a controller that can sense different temperature and power sensors all over the module, and also run operations like power capping so that we can keep the module under the thermal and rack power budget. This is the accelerator carrier tray. It has 2 PCI switches connected to 12 modules. In addition to connecting the accelerators to the host, the switch also enables a low latency peer-to-peer path between the accelerators, which is very important when we partition workloads across more than one ASIC. Other than the PCI part, the carrier tray supports the power from the bus bar to the 12-volt accelerators, and it has a lot of debug circuitry to allow us to do at-scale debug through USB. So there's quite a big USB network on the carrier tray as well to basically access the ASIC USB from the BMC. Some additional details on the carrier tray. This is a very dense tray. You can see this. We basically used every bit of space we have to stuff it with accelerators to optimize on the perf per watt. There's an onboard bridge microcontroller, which basically does the monitoring, firmware management on the board, and then reports that to the BMC, which sits on the LCM module. The CPLD on this board, in addition to doing standard power sequence and reset control, also flags power fault, power sequence failures, connection issues, connection presence failures to the BMC for easier monitoring in the data center. One interesting feature that our mechanical team designed for this is a tool which is shipped with every system to basically be able to plug out these PCI modules without really, without putting your hands into the system. The third tray that we have in the middle is a memory expansion tray, which basically can hold 8 CXL modules. Each CXL module is expands the memory by 4 DDR4. Each CXL module has 4 DDR4 devices, which can expand the host memory by 1 to 2 TB. Additionally, we have the baseboard is very flexible, so we've designed it to be able to swap some of those CXL modules with even.s flash drives, or also connect like a NIC, which basically connects to the same switch as the accelerators, so that allows for a low latency peer-to-peer path between the accelerator and this RDMA NIC. Refresh on the Grand Teton platform that we released a couple of years back. It's an 8 OU box with a CPU tray, a switch tray, and an accelerator tray. The accelerator tray is like a UVB compatible accelerator tray, which is like a GX, NVIDIA GX. So we made changes to this platform to basically support our use case. So we leverage the same BMC on SCM, same power distribution boards, the same ORV3 rack. We made some changes to wire the motherboard directly to the accelerator tray instead of having a switch tray to basically reduce the wiring in the overall system. Other than that, there's some changes to the CPLD logic to basically detect more faults in power sequence and power faults. So overall, this is an example of a base platform having a lot of flexibility, so then we can design, we can leverage the same platform to support different use cases. So that's something that we look for in our future platform designs as well. The specific OCP spec is in progress for the new blocks on the system. You can find the OCP specs for Grand Teton and the AMD motherboard on the OCP portal. Some additional details on the MTIA SIC itself was published in our blog earlier this year. So you can refer to that for more ASIC architecture details as well. Any questions?
Yeah, we have 7 minutes for questions. Please go ahead.
I have questions. So can you please elaborate what's the difference between this platform and the regular training platform and make it suitable only for the inference task only?
I think on this platform, if you look at the Grand Teton platform, the accelerators are basically designed to support inference workloads, so they're kind of lower power but more efficient. The memory, it's memory heavy so that we can support some of our higher memory requirements on the inference workloads specific to meta use cases.
Okay, thank you.
Just to follow up here,
Yeah.
In terms of the memory expansion for inference and if the CXL side is already deployed, or trying to understand a little more of the use case here also in terms of what do you use the memory for?
Sorry, can you repeat that?
Let me try and repeat it. Try to understand if you've already deployed the CXL. If not, when does it get deployed? And also trying to understand the inference use cases for CXL.
Yeah, we generally don't comment much on on the deployment config, but the platform is designed to support CXL expansion. We found that in some cases, some workloads, the host memory that we have with DDR5 may not be enough based on the so basically we are using CXL here to append the host memory for workloads which need a higher ratio of accelerator to host memory.
Maybe you can comment a little bit on CXL ecosystem, and if like you validate the system with CXL, and if all of the firmware, software, everything is in place already, that would be good to know.
Yeah, we did validate and qualify the DDR4 based expansion. So we, in our superset config, we basically have like a 2 TB on the host and 1 TB on the CXL, and that's something that we've tested.
Great, thank you so much.
Yeah.
Hello. What is the ratio of accelerator to OCP NIC in this platform, and is the NIC in its own right a bottleneck in usage of the platform?
Yeah, we've tried to basically make sure that nothing on the platform, like the CPU or the memory or the NIC, can become a bottleneck. So right now we have, I think, we have around 24 accelerators, around 400 gig bandwidth. I think at production, probably that's good enough, but yeah, that could become a bottleneck, including the PCIe as well as the NIC could become a bottleneck.
Okay, but the platform in its own right has how many NICs for expansion into
Oh, yeah, we have 2 NIC, I think you're referring to these expansion slots, right? We have basically 2 NIC slots for 24 accelerators, and each NIC slot can go to 400 gig.
Excellent, thank you.
Yeah.
Is there a reason you would want to scale out from just this node for inferencing workloads, whether it's like a bigger model with more parameters or just a need for higher throughput or latency, or is like one node enough and you just have a large front-end network connecting all of them?
Yeah, definitely. I think as the models get bigger, we have different use cases. We can run a workload on a single ASIC. We can use the P2P on the switch to basically make a fabric of 12 ASICs to run bigger models. There's definitely use cases coming down where we need to go out of this box to support larger models in that case.
Thanks.
Can you talk a bit about the workloads, inference workloads? You know, you have the Gen AI type of models, and you have the classical, you know, just image recognition and other recommender system kind of models. Do you run both Gen AI type of apps as well as general purpose, kind of the older type? Because, you know, we've heard that the inference for Gen AI sometimes needs cluster of GPUs, particularly, you know, from an NVIDIA perspective. So could you shed some color on type of workloads that you are running while inferencing on this versus, say, an AMD MI300X kind of system as well?
Yeah, I can probably comment on this particular system. So this ASIC itself is built ground up for recommendation inference for our apps. So the ASIC compute to memory ratio is optimized for recommendation models. If you have a look at the blog we have on the website, that goes into more details on the ASIC architecture itself. So the system design is built around to basically maximize the compute that you can drive on the ASIC. But this platform, to answer your question, is specifically meant for recommendation inference. No, just specifically for recommendation inference. Thank you.
Thank you, Pavan. Yeah. For those who want to ask Pavan more questions, we can get him on the side for those. Thank you.